This is a short demonstration of the N.I.G.E machine. We're using the N.I.G.E machine to conduct an experiment on an electronic circuit. The circuit's here, it's been built on a breadboard. Essentially it consists of a light sensor here and a variable LED here, which has 3 color components. And through these hookup wires it's connected to an output port on the N.I.G.E machine, which you can see here is just this development board. The development board is quite hardy, it's got buffers on its output, so it's quite feasible just to use these hookup wires to connect directly into a breadboard. The components on there, so we have, on this side we have an LED with 3 color elements, red, green and blue, and what we're going to do is send a square wave signal along each of these red, green and blue wires. The reason for using a square wave is that the LED needs to have a constant voltage, but by varying the duty cycle of a square wave, so varying the proportion of time when it's up and down within the wave, we can vary the amount of current on average that the LED is receiving and therefore how bright it is. The TAOS sensor, it's just Taos is the manufacturer. It's very simple. You can see here that basically it has a ground, VDD and an output. The output is simply, well, after light it hits the photodiode and then there's a current to frequency converter. You get a square wave and you simply count the frequency to measure the amount of light that's falling on the sensor. That's here, and via this yellow wire that's also being read by the N.I.G.E machine. So how does it work? Very, very simply, there is a digital layer, a digital logic layer between the electronic circuit and the computer elements. For the LEDs, it is simply a very, very simple series of counters which create the duty cycle, and that's interfaced with 3 byte memory locations which define what size duty cycle we want from 0 to 100, and simply produces a duty cycle of that size. For the light to frequency converter, we simply have a frequency counter here. It's a very simple process. It has a couple of clock signals in, then it takes the signal from the pin and it outputs a 24-bit value, which we read as a 32-bit value with leading zeros, which is the actual frequency. There's a debounce process here, there's a state machine for measuring transitions, and there's a very simple register process there which simply counts for a period of 1 second and then transfers the value counted to the register, which can be read. It's memory mapped into the CPU address space, so it can be read very simply by program code. So let's just quickly demonstrate that. If I take memory location 63521, that's the location of the duty cycle for red. So if I write a value of 100 into 63521 C-store, you can see the LED comes on with red light. I can actually define a word, red, which is going to take whatever value is on the stack and store that at 63521. C-store. Okay, we've just defined a word. So if I try 0 red now, let's just turn that off. I actually, before starting this demonstration, I actually created similar words for green. So let's put 50 onto the green LED, and we'll put 75 onto the blue LED. And you can see the green and the blue LEDs are both on now with variable brightness. So I'll just turn those off. How do we read the TAOS? Well, we simply read the value at 63524. Simply get that, take a look. And it's got a background count of around about 85,000 Hertz. So if we look at the table here, which is basically output frequency versus irradiance, you can see irradiance at the bottom, frequency here. So we're just below this line here. We're in the top area because there's quite a lot of background illumination, which corresponds to around about sort of just over 10, 12 on the irradiance scale here at the bottom. Of course, in a real experiment, this would all be shielded, etc., to cut out external light. But for the demonstration purposes, it's easy just to keep the lights on, and we can take a look at the linearity of this graph. The nice thing about working with the N.I.G.E machine is it's quite interactive. There's a 4th interpreter here, so we can play around and just get some ideas of rough values before we start the experiment. So I've actually defined the word TAOS to read this value from memory address 63524, and we'll do it now again with the lights off and just to reconfirm the background reading. Yeah, around about 83,000. So there is variation in the amount of background light, and which is another reason it would have to be cut out on a proper experiment. But we're seeing a baseline sort of in the low 80s essentially. And if let's put 100 on the green, so let's turn the green element full on and check, print that out. We're getting about what, 412 kilohertz. So we're seeing we're seeing a fair range there depending on the brightness of the LED, which is what we want. And this is quite interactive. We can sort of play around, test components, etc. quite interactively. I am going to define a word test now. What test will do, it'll take whatever value is on the stack and it'll write it to the green element, and then we will wait for 2 seconds. That's because it takes a second to make a reading, so that if we wait for 2 seconds, we're certain to have a clean reading after changing the brightness of the LED. We'll wait and then we'll do a reading, and that will complete our test procedure. Okay, so that's defined. And again, the idea of interactivity. So let's test this thing at 50. So let's do 50 test. It's reduced the brightness of the green LED. It's 2 seconds. It's done it, and we'll just print out the result. It's about 246. Call it 250 kilohertz. And so you can see we're now in the range. It's not halfway, but this is the experiment we're going to test. So we'll define the word experiment. What this will do, we're going to repeat a series of tests now. So we're going to go from 0 to 100, so 110 will be our stopping value, and we're going to do a do loop here. What we'll do, we'll call up the loop counter, duplicate it, print it, and then we will test with that value of the loop counter, and then we'll print the result, and then we'll go up increment of 10 just to make it quick. We'll just have sort of 10 samples and then plus loop. Okay, we've finished defining the word experiment, so let's watch the experiment unfold. So 0, it's now doing the measurement. 84,000, 10, 114,000, 20, 146,000, 30, 179,000, 40, 211, 212,000, 50, 245,000, 60, 278,000, 70, 311, 80, 345, 90, 379, and 100, 414,000. So in the interest of time, we won't take it further here. But what you can see, we've basically got quite a simple platform here where you can build a circuit on a breadboard. It interfaces very simply via sort of hookup wires in this temporary situation with the expansion ports on this FPGA development board. And then the interesting point is you can define your own digital logic layer, whatever components are most appropriate, give you the most flexibility or the highest speed of response. In this case, we have a frequency counter or duty cycle creators. And the point is that the CPU is not needed for maintaining the electronic interface. This is all happening automatically in parallel with the CCU. The CPU doesn't have to participate in that at all. And then using the fourth interpreter and compiler, it's possible to sort of interactively bottom up build experimental code, which is much simpler for testing and development than having to go through a tool chain and try little routines to compile here, to download into the machine, etc. And then once it's ready, it's possible to do experiments. There's an SD card reader here connected to the N.I.G.E machine, which can be used for saving values, etc. And so this is the principle for using it as a testbed for scientific applications. Thanks very much for watching.